Hello, and welcome to the Introducing the New OpenNebula MCP Server screencast. The Model Context Protocol is the protocol designed to function as a universal standard for communication between LLMs and external tools. Its core purpose is to provide a structured and secure framework that enables an AI agent to augment its capabilities through the interaction with diverse systems and APIs. Model Context Protocol is built upon three foundational principles. It established a universal protocol creating a standard communication bridge between a large language model and any external tool. This design eliminates the need for custom, single-use integrations for each new service and ensures broad interoperability. MCP enables an AI to discover and operate tools within a controlled and secure environment. This framework includes built-in mechanisms to prevent unauthorized actions, manage permissions, and ensure user trust and safety during the tool execution. Protocol transforms the AI from a passive conversational entity into a proactive agent. It provides the capability to autonomously execute complex, multi-step tasks by interpreting user intent and coordinating the required tool operations to achieve a goal. The management of modern cloud infrastructure presents significant operation challenges due to its inherent complexity. The complexity manifests across the primary interfaces used for cloud administration, leading to widespread inefficiencies and increased operational risks. Three key challenges define the current landscape of cloud management. Graphical user interfaces, while intended to be user-friendly, are often characterized by deeply nested menus. The design reduces user productivity and impedes the ability to perform scalable and consistent operations, particularly for the repetitive tasks. Command line interfaces offer powerful control but are associated with a steep learning curve. The necessity of mastering provider specific syntax and intricate command structures increases the risk of manual errors, posing a threat to operational stability. To overcome the limitations of standard interfaces, organizations frequently resort to developing custom automation scripts. This practice increases long-term maintenance overhead and results in fragile, non-standard operational workflows that are difficult to scale. The OpenNebula's MCP Server is an AI copilot designed to streamline cloud administration. It functions across an intelligent layer that translates natural language commands into direct cloud operations, addressing the core complexities of modern infrastructure management. Its capabilities are delivered through the three primary mechanisms. The system leverages advanced AI to accurately interpret natural language. It is engineered to translate high-level user objectives directly into executable operational logic, moving beyond simple command parsing to understand the goal-oriented requests. The MCP server can execute complex end-to-end workflows from a single natural language command. This capability eliminates the need for manual scripting and direct user intervention for sequential or conditional tasks. By providing a simple conversational experience, the server effectively replaces the need to interact with complex GUIs and CLIs. This approach makes cloud management more intuitive and lowers the technical barrier to entry for all users. Let's quickly walk through the one-time setup process. Our goal is to get the MCP server and the MCP client talking to each other. In the terminal, we'll set up the OpenNebula MCP server. This is a quick three-step process. We're going to clone the repository, install its dependencies, and then run it. Once we have tested that the server is running correctly, we'll switch to the Visual Studio Code. In the Visual Studio Code, we also are going to install the CLINE extension, configure the connection, and then send our first request to confirm that everything works as expected. We have the OpenNebula command line installed and configured using the environment variables. We are pointing to the correct OpenNebula RPC API server and one auth file that contains credentials. Necessary software is on the GitHub, so we must clone it first. Also, we should install and prepare the virtual environment to run the MCP server. Run the main.py to launch the MCP server. Next, we're going to use the Visual Studio Code with CLINE plugin to provide a conversational interface. To verify that all is set, let's ask to list all VMs in the environment. You can see that the API call has been executed. In this demonstration, we are going to showcase the difference between inspecting your environment in the old-fashioned approach using the command line and OpenNebula MCP Server. In the traditional way, to get a full picture of your cloud infrastructure, you have to run a series of separate commands for hosts, then for VMs, and then for networks. And the most challenging step is to parse and extract the necessary information from the output. Then let's compare it to MCP server approach that only consists of two steps. Firstly, ask the correct comprehensive question and then get the output in the expected format. Let's list the hosts that are currently configured in our environment. Doesn't matter whether the output is formatted in the human readable format or JSON or XML, it's still a lot of data. Without parsing the output, you may get easily overloaded with the data. Let's see how easily we can achieve the same result using the MCP instead of a manual command line interaction. We're also going to request structure the data in a readable format. As you can see, the MCP has responded with a structured, easy to understand information on all three requests in a single shot. Next, we are going to tackle a very common task, deploying a new web server. In this case, the approach differs by a margin. Instead of telling how to do the job, you are describing the desired outcome. Traditionally, the workflow is a manual, multi-step process. You have to extract the correct ID, use the ID to instantiate a virtual machine, and then manually execute the web server software installation. On the opposite side, the MCP server allows to replace the set of multi-step command execution with the two prompts. First prompt, you request a server with specific parameters, and the second prompt is to install the desired web server software. To perform the task in the command line, we must locate the template first using the oneTemplate_list command. Then we must instantiate the desired template, supplying it with the additional parameters like name and virtual network attachment. It may take a while before we can connect to the virtual machine, but eventually we are getting there. Now let's also install all of the updates, as well as we must install the Nginx web server. Now let's connect and verify that we can access the default web page plug. Let's compare it with the MCP way. Let's write a prompt that we want a VM that is based on the Ubuntu 22 with network card placed into the service network. In terms of resources, we want to have one CPU and 2 gigs of memory. Also, don't forget to name it as MCP Web Server. The MCP has eventually succeeded in the given task. Currently, VM is in the prologue state, which is one of the deployment phases. Let's ask MCP to install the software we need. As you can see, MCP is not just a helpful assistant, but also is capable of executing commands inside the actual virtual machines. And now we can access the web server's default web page, although this time all set of operations were performed by MCP. Finally, let's look at the troubleshooting of a common application failure. This demo showcases a fundamental shift in how you can debug and solve issues. In the traditional method, you are going to manually connect to the machine, locate and edit a specific configuration file, and finally restart and verify the fix. It's a hands-on process that requires direct input. In the contrast, the MCP server approach is radically different. The user simply describes the issue in a single sentence. The MCP then takes over, autonomously handling every necessary step: the diagnostics, the correction, and the confirmation. Let's try accessing the web server ourselves to verify that the problem is not on the user's side. Indeed, the web server cannot be accessed. By logging into the shell, we can locate that the web server is not running. By digging deeper, we can locate some errors that had prevented engines from running. A config file is not set properly. Let's fix the missing semicolons and try to start engines once again. Now the engines is running and we can verify it by connecting to the web server using curl command line. Let's try to achieve the same goal, but this time with assistance of MCP. Now let's ask MCP to assist us with the troubleshooting by sending the prompt that our web server with virtual machine ID 720 is not working and we need to fix it as soon as possible, keeping the solution as simple as possible. It's worth mentioning that MCP can be either on autopilot or ask for approval of any action. To foster community engagement and transparent development, several resources are available for the MCP server for OpenNebula. These resources provide clear pathways for users and developers to participate in the project's evolution. The project's feature development is outlined in a public roadmap. This document details planned enhancements and allows the community to review and provide an input on the prioritization of new functionality. The complete source code is managed in the official repository. This allows for direct inspection of the code, tracking of all development activity, and submission of pull requests for review and integration. A dedicated section on the official OpenNebula community forum is available for public discussion. The platform serves as the primary hub for users to ask questions, share use cases, and interact with our core team. This screencast was produced in the scope of ONEnextgen project. Thank you for watching and see you in the next screencast.